Essay 4. The Farm Fab Lab, Digital Fabrication at Agricultural Scale. February 19, 2026. Anno Domini. Agriculture is often imagined as ancient, cyclical, and resistant to rapid technological change. Fields follow seasons, livestock follow biological rhythms, soil responds slowly to intervention. Yet beneath this perception lies a long history of innovation. From steel plows to GPS-guided tractors, farms have consistently integrated technology to increase resilience and productivity. The next logical evolution is not larger machinery, but smaller, localized intelligence, the small-scale digital fabrication lab embedded directly on the farm. A farm-based digital fabrication lab, often called a Fab Lab, is a compact workshop equipped with tools such as 3D printers, CNC routers, laser cutters, microcontroller workstations, and basic electronics assembly stations. Unlike industrial manufacturing facilities, these labs are modular and adaptable. Their purpose is not mass production, but rapid prototyping, repair, and customization. At first glance, fabrication labs seem more suited to urban innovation hubs than rural landscapes. Yet farms operate as complex mechanical ecosystems. Irrigation systems break. Feed dispensers wear out. Specialized brackets and fittings fail. Waiting for replacement parts can delay operations during critical planting or harvest windows. A localized fabrication lab changes this dynamic. Instead of ordering and waiting, a farmer can measure, design, and produce a replacement component on site. The economic implications are significant. Agriculture often operates on narrow margins. Equipment downtime carries direct financial cost. A small-scale fab lab reduces dependency on external supply chains, especially in remote areas where delivery delays are common. By fabricating custom parts, farmers extend the life of existing machinery rather than replacing entire systems prematurely. Over time, the lab becomes not just a convenience, but a resilience asset. Beyond repair, digital fabrication enables innovation tailored to specific terrain and livestock conditions. No two farms are identical. Soil composition varies. Barn layouts differ. Microclimates influence planting strategies. With digital tools, farmers can prototype specialized seed spacing devices, livestock monitoring mounts, irrigation adapters, or ergonomic tool modifications suited to their unique context. Innovation shifts from generalized manufacturing to hyper-local problem-solving. Electronics integration adds another layer. Microcontrollers and sensor systems can be assembled and deployed directly from the lab. Soil moisture sensors, automated greenhouse vent controllers, livestock health monitors, and solar-powered field data loggers can all be designed, tested, and refined in-house. Rather than relying solely on proprietary agricultural technology, farmers gain the ability to understand and modify their own systems. This decentralization of fabrication mirrors broader shifts in technological philosophy. For decades, manufacturing consolidated into large-scale global supply networks. Efficiency increased, but dependency deepened. A farm fab lab represents a modest counterbalance, not rejecting global supply chains, but supplementing them with local capability. It embodies a hybrid model: global knowledge, local production. Education becomes a parallel benefit. A small fabrication lab on a farm can function as a learning environment for family members, local students, or community groups. Youth exposed to both agriculture and digital design gain interdisciplinary skills. They see firsthand how software modeling connects to soil cultivation. The boundary between tech and farm dissolves. This integration may inspire a new generation of rural technologists who view innovation as compatible with stewardship. Energy considerations also align naturally with agricultural settings. Farms often have access to solar or wind resources. A modest solar array paired with battery storage can power fabrication tools, creating a semi-autonomous workshop. The lab itself may fabricate mounts, enclosures, and wiring guides for renewable systems, reinforcing a cycle of localized sustainability. Importantly, a Farm Fab Lab does not industrialize the farm into a factory. Its scale remains intentional. The goal is adaptability rather than volume. A 3D printer may produce replacement bushings or irrigation couplers. A CNC router may cut plywood components for storage systems. A laser cutter may create precision gaskets. These outputs are small but impactful, reducing friction within daily operations. There are limitations. Not all agricultural components can be fabricated in-house. High-stress mechanical parts may require industrial metallurgy. Safety standards must be observed, particularly when fabricating load-bearing or food contact components. Digital literacy is necessary to operate design software effectively. However, these constraints do not negate the value of incremental capability. The broader philosophical significance of a Farm Fab Lab lies in autonomy. Modern agriculture is deeply intertwined with globalized equipment manufacturers, seed suppliers, and chemical producers. While this interconnectedness enables scale, it can also constrain flexibility. A digital fabrication lab restores a measure of agency. Farmers become not only operators of machines, but designers of solutions. This model also supports collaborative networks between farms. Digital design files can be shared regionally. One farm prototypes a durable fencing clip, another refines it, a third adapts it for different livestock. Knowledge circulates digitally while production remains local. The farm community becomes a distributed innovation network rather than isolated operations. Resilience is increasingly important in a world shaped by climate volatility and supply chain disruption. Extreme weather events can delay shipments. Economic fluctuations can alter equipment availability. A small-scale fabrication lab does not eliminate risk, but it reduces vulnerability by shortening response time between problem and solution. There is also a cultural dimension. Agriculture has long balanced tradition and experimentation. A fabrication lab embodies this tension. It sits beside barns and silos, not in contrast to them, but in dialogue. Steel and circuitry coexist with soil and seed. The farmer, historically seen as laborer and steward, increasingly becomes technician and designer. In the long term, farm-based digital fabrication could contribute to broader rural revitalization. Workshops become hubs of creativity rather than merely maintenance spaces. Local repair economies strengthen. Small manufacturing cooperatives may emerge around agricultural innovation. Rural areas gain technological infrastructure without sacrificing identity. Ultimately, a small-scale digital fabrication lab on a farm represents convergence. It merges physical production with digital design. It blends agriculture with computation. It supports resilience without abandoning interconnection. It acknowledges that progress in farming does not always mean larger machines or centralized systems. Sometimes it means equipping a small workshop with the capacity to imagine, prototype, and build. The Farm Fab Lab is not futuristic spectacle. It is practical infrastructure. It reflects a philosophy that technology should serve locality rather than erase it. In doing so, it quietly redefines what a modern farm can be, not only a site of cultivation, but a site of creation.